Hello, my name is Brandon Reznicek, and this is my presentation for Lab 3, Determining the Mass of a Black Hole. The purpose of this experiment is to analyze given position data of a star orbiting a black hole, and use this to determine the net force acting on the star, which in turn allows us to find the mass of the black hole. We developed a computer model using Python, in which Newton's second law is applied to given position data in order to estimate the net force acting on the star, as well as the parallel and perpendicular components of the net force. Afterward, by applying Newton's law of universal gravitation to the data we obtain from our program, we can solve for the mass of the black hole in our problem. The main underlying physics principles in this experiment are Newton's second law and Newton's law of universal gravitation. Newton's second law tells us that the net force acting on an object is equal to the object's mass times its acceleration. This can be rewritten as mass times the derivative of velocity, which is the same as the derivative of momentum. We also know that the parallel component of the net force is equal to the derivative of the magnitude of the momentum. The perpendicular component of the net force is equal to the magnitude of the momentum times the derivative of its direction. Newton's law of universal gravitation tells us that the magnitude of the gravitational force acting on an object is equal to the gravitational constant g times the mass of the first object times the mass of the second divided by the distance squared. But how do we solve for net force given only position data? All we need are three position vectors separated by a small time interval. From these three position vectors, r0, r1, and r2, we can calculate two velocities, v0 and v1. From these two velocities, we can calculate a change in velocity. This allows us to calculate a change in momentum by multiplying the change in velocity times the mass. Finally, we can approximate dp dt, the derivative of momentum. We know that dp dt is equal to the net force. Here we have the code for our model. The first part of the code randomizes the position data points based on a seed we input. Next, we have our algorithm for computing the net force. First, we must input the star's mass, which we know is equal to 2 times 10 to the 30 kilograms. Next, we must specify a delta t, which is a time interval between our data points. In our case, delta t is equal to 1 day. Next, we have a while loop, which calculates the velocity from our position data points. First, we calculate the x component of the displacement and divide it by delta t in order to find the x component of the velocity at that point. We do the same thing for y in order to find the y component of the velocity. The next loop takes these velocities and calculates the net force at each point. First, we get an initial velocity and a final velocity. Next, we find an initial and final momentum by multiplying these two values by the star's mass. Next, we calculate delta v, which is equal to v final minus v initial, and delta p, which is equal to p final minus p initial. Once we have delta p, we can solve for dp dt by dividing delta p by delta t. We know that by definition, F net is equal to dp dt. This allows us to obtain the net force at each data point. The next steps calculate F net parallel and F net perpendicular. First, we calculate the unit vector p hat by dividing p initial by the magnitude of p initial. Next, we calculate the derivative of the magnitude of the momentum by subtracting the magnitude of p final minus the magnitude of p initial and dividing by delta t. This allows us to find dp dt parallel, which is simply equal to the derivative of the magnitude of p times p hat. dp dt parallel is equal to F net parallel. Next, we can calculate dp dt perpendicular by subtracting dp dt minus dp dt parallel. Once more, we know that dp dt perpendicular is equal to F net perpendicular. Finally, we print out the data we need in order to calculate the mass of the black hole using Newton's law of universal gravitation. Let's take a look at our model. In our model, the yellow sphere represents our sun, the black sphere represents the black hole. The yellow arrow represents the net force, the black arrow represents the parallel component of the net force, and the red arrow represents the perpendicular component of the net force. Our program also outputs the final magnitude of the net force acting on our star, as well as the distance between the star and the black hole. We can plug these values into Newton's law of universal gravitation in order to solve for the mass of the black hole. We found that the mass of our black hole is equal to 1.314 times 10 to the 35, which is an enormous mass. As we mentioned before, the net force and its parallel and perpendicular components are exactly the same, by definition, as the rate of change of momentum and its parallel and perpendicular components. Newton's second law tells us that dp dt is equal to the net force. In our case, however, we're assuming that the delta t we're using as time intervals between our data points is small enough that delta p over delta t can be an approximant of dp dt. If the black hole whose mass we found was removed and a different black hole was placed in the same location, and the motion of the observed star remains unchanged, we can say with certainty that the mass of the black hole is equal to the black hole that was previously there. If the mass of the black hole were different, then that means that the magnitude of the force acting on the star would also be different, which means that the sun would follow a different motion. In order for the motion to remain unchanged, the mass of the new black hole must be equal to the mass of the old one. In conclusion, by using Newton's second law, we can find the net force acting on an object from position data points, as well as the parallel and perpendicular components of the net force. In our case, where a sun is orbiting a black hole, we can then use Newton's law of universal gravitation the magnitude of the net force we calculated, and the known mass of our sun to calculate the mass of the black hole which it's orbiting. We found that the mass of our black hole is 1.314 times 10 to the 35 kilograms.